All right. We're live for day 13 of Add Enough Code. And notably, as you can see on my screen here, I've not quite finished day 12 yet. um, let's see, was it? So here's where I left on my part 2. I I have it working logically, and I still need to get Memoize to work properly. And my thought here is that I'm going to abandon elements of this approach altogether. So my basic unit was this kind of matches function that returned um, sort of the remaining strings, the possible remaining strings, or in this case indices, after matching a certain range of damaged springs. Right? If you recall last night here, um, we have these records, and we have a question mark if you don't know if it's damaged or undamaged, and then this means damaged, the dots mean undamaged. So we have all these blocks, right? We say we have a block of 1, 1, and then 3 damaged. And I think one thing I'm going to change tonight is instead of first doing these, instead of first doing these matches, and then sort of returning the remainder of the string, I will do like sort of a count. I'll do a recursive call of like count of my counting method rather than a recursive call of my matching method. All right, so what I memorize is not all these strings, but the counts instead. And as I do that, I'm going to rewrite a lot of elements and hopefully have it be a little bit cleaner. So let's go for that. Um, this is all going to be deleted. If we need to reference anything, we can look at our part 2 file that we had started last night. Oh, I mean, we have a parse function. I think we want to copy that over. Def parse. Yeah. This gets you the string and the list of integers. And one thing I thought about doing to handle edge cases is to just add a little dot here at the end of my strings. It'll be more obvious later why I need that. Oh my god, I still have a cough. So we parse. We have a function, something like def count. I guess we can just call it counts. We're counting arrangements. So given a string, I might put my parsing inside of this method. Nah, we'll just pass on the string. So we have the record. So what is this row called? Condition records. So let's call this a record string. And then there are two parts of the record. So there's the redundant side and the right side. And what's it called? Condition records of which is damaged and operational, or unknown. And then we'll just call this the groups of damaged. And I guess we're also renaming these things. So conditions, record, and then we're renaming that to groups. And now getting this to work for part one will be easy. We don't need the memo, but we're going to do this thinking about how to make this memoizable. And I think we will memoize sort of at this level here. I might have another parameter, which is how far in the string we're going. Could just pass it a. I'm probably fine just passing it a string. If we're calling recursively, um, one other insight I thought was that the memo doesn't need to be kind of external to this function. It should be individual per run of this function. Yeah. So yeah, individual per run of this function because each record is going to have, there's not going to be much reuse between each of these records. And then it prevents me having to have the whole string as part of the keys. Then we just have like keys or indices, etc. So let's have a memo, mutable empty, and this could be string int int. How did it know I wanted a second int? No, we want a group of int. To int. And then we have our search, which is going to be this is what's going to be memoized. So yada yada. That's not quite what I wanted. Yeah, like a from index. And I'm just going to anticipate this in advance. This is going to return a long. So this also returns a long. I'm still probably going to break out a smaller function that takes just one of these and looks at all the possible matches, return all of the indices for where that group match can be. Yeah. So we're going to start with, we'll have like a calculate value in here, and this will be a long, and for now it's just triple question mark, but we're going to use a memo like else update record from groups and calculate. Because this search here, will potentially be recursive. Okay, so for that calculate function, we're going to need to see def match ranges. Yeah, it's the various ranges that the match can cover. So we have the record. We have a from index, and then we have a group size. And yes, this will return a list of int. Okay, so we have a from, and then we have a last possible from. And that will depend on a few things. So first, there's the index of the next damaged piece. Well, we call it last damage or next damage. Starting from. And that could be a -1. And then Yeah, that will help us calculate our last from and our potential last until. So if we're drawing this out here, let me make this bigger. In fact, I'm just going to full screen the whole thing. So we have our example. Let's say we have a bunch of question marks, and then there is a couple damaged pieces, and we're matching up to 4, right? So the last potential from we can get from here, this case, is all the way over here. And this start here being the first from, or whatever this from here we give. And it'll be a condition of this function that there are no undamaged pieces in this range. Or will it be? That we'll come back to that. Okay, so what else could happen? Potentially, this could end, right? We could have a dot right here, in which case the last until that we could have is going to be a location of that dot right there. There's also the case that we reach the end of the string altogether. But since the end of the string is always going to have a dot, then we are fine there. Now, I think there might have been another case, so I'm just going to check my other file. Last potential, there's going to be like a list. We're filtering for like -1 somewhere. Oh, we don't have it anymore. Okay, here. Working. There's the match limit. Okay, we were like looking at the length. This kind of is the same as first damaged. Oh, wait. Okay, index of a block that's larger than this. I don't think this actually matters because all that's really limiting us is that first one. And then afterwards, we'll check that the piece after the until is not, is still, it is not a confirmed damage piece, right? So indices equals from, oh, wait, we have to have the last until. So record dot index of, I suppose the dot. Yeah. Yeah, that works. And index of, yeah, it's index of a string. Cool, cool, cool. And I suppose we determined we can choose between these two, right? Like we subtract group size to get whatever last from this turns into. Let's give this an actual name. Limit. I don't know. Undamaged. This is next undamaged, sure. And val last until equals the min of two things, which is next next undamaged dot min next damaged plus group size. And then now we take from until last until, and we're going to map on that. And And we do, actually, I think we just filter on that. So dot filter, and what we have to check in each of these cases is that all the from pieces are, excuse me. Oh, I don't think we even need to check everything within that range because we have the index of the next dot, right? Which might limit us in and of itself. So we take this I and we check that record I plus group size is not equal to that exactly. Okay. And let's try this out on some things. So we have match ranges. Let's try something smaller. So question dot this is pound, and then question. And let's start from 0 and group size of 1. So what are the potential indices for this group? Oh, whatever's going on here needs to be what is there? Found unit required long. This does return a calculate here would return a long. We pass in the key. I don't understand this type error. Found unit required long. This is a long. I'll just question that, mark that out for now. Oh, here we go. It's still saying found unit and required long. I don't know, like, so we have a weird syntax error of some sort here. Oh, hold on, this outer count function. Okay. So we have search records starting from 0, and then we just pass in the groups. Okay, we defer to the memoized function that will be recursive in our broader count. Okay, so that works. Interestingly, so this should have exactly one solution, and we are not finding that. Well, no, it should have 1, 2, 3 solutions because it can be the first question mark, second question mark, not the third, because that would make a block of size 2. So we're expecting this to equal list of 0, 1, and 3, right? Oh, these here could be negative ones. That's the issue. So we need to take these list next undamaged, next damaged dot filter not equal to -1, and then take the min of that. Okay, great. So this is working to some extent. Let's print whatever this range is. As we do that. So these are our potential starting points, right? 0, 1, 2, and 3. So all of those might potentially be valid. And for each of those, we check that the record in I plus the group size, so that's, 0, 1, 2. It shouldn't be until 3. It should be 2, 3. Oh, yes. It should be 2, 3. Yeah, last until is kind of a a misnomer here. Okay, that'll make that work. We'll do a to-do, rename these. until is misleading. Okay. Where do we go with that? Let's just do a couple more tests. What if we had a group of size 3? Um, Now it should be able to expand further. So 1 takes these 3, 2 is these 3, 3 is all of those. Okay, now let's do a test with some dots in there. So let's say there is a dot right here. Now we should have only 2 solutions. Oh, interestingly, we still have 3 solutions. So let's just make that a thing that we'll test. Dot size equals 2. And now if there was a dot beforehand, then okay, it should be smart enough to try to skip past that. And it should still get 2 solutions. So this should also be dot size equals 2. So all that matters then is the dot after the next whatever. Yeah, good to know right now that that's not correct. Um, I might come back to this in a sec. We'll debug that. Let's think about how this whole thing is going to be structured. So let's take let's, let's take some indices from using that match ranges. So val match ranges, and these indices specifically are like the starting are the starting indices. I think we only care about the first group. So this might be like a groups.fold left. And I still don't know about the case where it is, I'll leave a big to do here. We'll just default that to 0 for now. And we'll think about that later. So we have like group size, we have, what exactly are we accumulating? I guess counts. Yeah, yeah, the sum of all of these recursive calls. These recursive calls that will not be tail recursive because they're being folded up and summed. But that's probably fine. We're probably not going, right? Like, what's the longest size of any of these? We're probably not going 10,000 deep. We'll just call this C for right now. I don't want to shadow the actual number. You know, we can call it count. We can shadow that. Great. So now we take like the match ranges. Or not val, rather. We're just gonna call it match ranges on this record, starting with our from, and we pass this on to like recursive calls. I don't know why exactly this is quite a fold left. We just map across all of those. Yeah. And in fact, this here fold left, I might turn that into like an if else into a recursive call of search. So let's start with a map here. Dot map. So we have some I. We have our group size. And we can search I plus group size. Great, we're taking off. We're basically incrementing it for past, I think we can do a +1 as well, right? Let me think about that. So we have, let's say we just match those three right there. So this is at index 3. Um, it's of length 3, so 3 plus 3, that's going to go up to 6. It's going to start us here, but we don't want to start searching for anything here. So we need to add that +1, that buffer space. I have this group size +1. And we search for groups.tail. So all of these then end up being summed up, which is, I guess, why this would make sense as a fold left. um, yeah, we'll call them recursive counts. And then the answer to this is just recursive counts.sum, right? But it's using this memoized search into there, which hopefully gets used a lot. Let me see here. I kind of want to count accesses into the memo, just so I know how it's performing. But maybe I'll do that later. Yeah. Give me a sec. I'm gonna get myself a cough drop while I'm thinking about this one. Now there is this outer fold left. And I suppose this is like a fold left on the groups themselves. We don't need to do that because we're passing groups.tail onto here. So this is basically a match of like if it's empty or not. So if groups is empty, then something. Otherwise, oh, we have a cat trying to get into my room here. Otherwise, yeah, this count and group size for. Oh, where's this count coming from? We don't care about this count. So this is going to be like group size or groups.head. Yeah. And then we pass on the tail over here. Okay, that's what our recursive structure looks like then. And that would, I think that on its own would do it. Again, I don't know if this memoization is what will save me. But first we have to fix this. So we have some test cases that are failing. When the dot appears before a damaged piece. What I could do is just make sure there is no dot in the range that I'm considering taking. So let's take these. So these are our froms. Now froms was from the last until. You just call this the last from, right? The last starting range of the whatever. That kind of makes sense. Okay, and froms we're going to filter this. And then case, I guess we call it, let's work with I. We're going to do something similar to what we have so far. Um, this next undamaged, we're not going to use right now. In fact, let's do this. So from.filter, we're just going to comment out this previous version. Okay, so next undamaged shouldn't matter. We would just go to the end, I suppose, if there were somehow no damaged pieces in front of us. And we could search like I indices, but we could search indices that are undamaged or operational. Yeah, let's do from until record.length filter, or like all the indices indices where actually, I mean, these are indices. That filter record of that was equal to a dot, right? And now the last from. So if we knew like how many needed to follow this, we could optimize this further. But for now, I'm just going to go until the end if we don't have an index of a damaged tile, which, might very well be the case, but is probably rare. Of course, in those rare cases, it could spike up my calculation time, but we'll handle that when we get there. The last from, it's going to be if next damaged equals -1, then interesting. We could use the operation indices. No. No, we're not going to do that. We're going to do record.size length minus damaged minus group size. Okay. And then now this filter becomes a bit more aggressive. So now everything should not, let's do I to I guess it's going to be until I plus group size. There's going to be these two conditions. Which I'm going to put here on separate lines. We'll call this so we'll call froms the filtered froms. And what we'll return is froms.toList. And this condition, so this is called none operational. So none operational within that range. And we're going to take this range here and we're going to do that for all operation indices that contains, or rather not contains. So let's say not exists any operational indices. Yeah, that should do it for us. And then what is this check called? Val damage. We need to make sure it's not extended. So not damaged after is what we'll call that. Oh, look, and my word lengths line up. The record I plus group size should not be equal to that. And that is our filter condition. This is called operational. I was gonna turn this into a set. Okay, let's see how that works. We have issues down here. Okay, we have some compile errors to fix out first. So recursive counts, what is this supposed to end up being? So match ranges int groups.head. What does it not like about that? Found strings and int we required int. Here. Match ranges. Oh, right, because we defined match ranges here. Why did we define that? We don't need to define that. We just do. Wait, where did this even come from? I think that's code as writing that I abandoned. Yeah. And group size is going to be groups.head. Okay. Okay, things are compiling. Let's see if these are working. Great, so it's working for all of our cases now. This is going to be indices 2 and 3. And this here, well, this above it is going to be indices 1 and 2 as potential match areas. And it knows to skip over whatever. I think we can test this on the example input. So let's do that. We are operating on the example input. So input.map parse, and we're gonna map count tupled dot sum. Let's just see if we get 21 there. Oh, not implemented there. Right. If groups is empty. Yes, in our base case, what is it? So if groups is empty, then if the record contains no more damage tiles that have to be matched after from, then then this is a solution. We can return 1, right? Oh, hold on. Yeah, that's a solution. Otherwise, it would be 0. The Blackzilian, thank you for the follow. Welcome. Are you doing Advent of Code yourself? So we look at this. If record index of that from is -1, then 1 else 0. It knows what I want to write. Okay, great. Now we have a string index out of range. Ah, yes, yes, yes. You're kind of new on programming. All right. Well, actually, in that case, add no code is a good place to learn. I mean, some of the problems would be hard for someone that's new, but you have hundreds of solutions to look up, different solutions from different people and different languages, um, tutorials and whatnot. Everyone's doing it. Okay, we have an index out of bounds, and I think I know where I'm getting that kind of a problem. And that would be up here in my match ranges file. Wait, what's this? Unused local definition. Yes, I don't want that anymore. So we should have another filter on my last from, and I suppose it could be based on the length of the record, right? Yeah. And we could do like a min. So we could define it like this. So option of, what is it, next damage? Not. And when we take the min of this, or we got a list. List of next damaged. And what is it? Record minus the group size. That's a potential last from. Is there a -1 in there for the buffer? I think there's a -1 in there for the buffer. Right. Uh, yeah, -1 or not, I think it'd work the same way. So filter not equal to -1, and then we'll take the min. Without last from. Record.size minus group size. Okay, our answers here are still working, and we get 21 for part 1. And let's test that on our real input. And we get 7916, which I believe was the answer we had gotten for part 1, 7916. Excellent. So already, this is at least simpler code than what I'd had before. I don't know, it's easier to debug. It's easier to think about. And most importantly, it'll be easier to optimize. So we're just gonna move our tests like down to the bottom. We want to keep them in there in case we screw things up somehow. And then we have a parse2 method now. So let's write that. And now we have a list.fill 5 elements of record. I'm gonna make string, combine them with a question mark, and add the dot at the end. And then it's just a list.fill 5 times contiguous damage, and then we're gonna flatten that into one list. And this is gonna be parse2. Okay, and before we test that, we're gonna test on the example. Make sure that's working properly. So this is val ends 1, val ends 2, use parse 2. Five two five 152. That is an answer I recognize. And there I just do this. I don't dare just do this. We're gonna test. We're gonna test this on some problematic lines. D12, 2023. Oh, nope. D12, 2023. Here we go. Okay, I remember line 5 here being problematic. So input 4, right? This line right here. No, that's not the one I'm thinking of. Oh wait, are we still in the example? Yeah, we're still in the example. Okay. Okay, and we're gonna parse that. So input 4, parse 2, or parse 2, input 4. Wait, parse 2 that. And then we're gonna count that. Count that twofold applied to the result of parsing. And let's see if we get, oh my god, we got an answer reasonably quickly. Does this just work? Oh my god, it just works. Ah! Oh, I figured it out. And it was so easy. It was so much easier. I wrote that all from scratch in, I don't know, like 50 minutes. When did I start? I got on at like 10:20. Yeah. Oh, that is great. That feels good. That feels good. That's some redemption right there. Yeah. Let's copy this. There we go. There we go. I'm happy. I'm so happy that worked. Wow. It was so much easier that way. So much easier that way. Okay. So I'm gonna commit this. Day 12. Let's see what changed. Everything changed. Thank you. Thank you, Zombie Show. Zombie Shoe. How's your advent of code going, by the way? And all of you, are you aware of my leaderboard? You should join. So I could see your lovely names riding above mine. So we're gonna commit this. And what's this? 2023 day 12 part 2 as solved on stream, and we're gonna do a little bit of cleanup. Good. It's good to be excited. Okay, so we didn't need this AOC import here. We have parse 2. This probably can be cleaned up a bit, so I'll think about that. Ends 1, ends 2. These tests we no longer need. We delete them. Like a good developer does, we delete our tests. Okay, so we have next image, which could be -1. We have these operational indices. I'm just gonna call this operational. Yeah, that's fair. That's fair. And then the last from. We're doing this way. And we check that nothing is operational, and we check that it's not damaged after our little range. Honestly, I think that's fine. That's fairly legible. This, I don't know, like this could be a fold. It never needs to be a fold. But then we can name groups head size. So let's see what that looks like. So groups.head option fold. And then this is like the default case here, which I don't like putting that big old thing. Yeah, honestly, I'm happy with how that reads. Didn't really change anything. I just deleted some lines. So I'm gonna go back to whatever is my commit. What did that change? Yeah, deleted some lines, renamed a thing, deleted some tests, sure. And I'm gonna say that's how I solved on stream. And we're gonna push. And if you'd like to see my code, it's all here on GitHub at that link. If you're coming in from YouTube, that's just in the description. And if you want to share your solutions, which I'm excited to see, I think someone already submitted one, please share them with me on Discord, or like we can chat about the problems generally. And let's see what other people did. Oh, I'm happy with this. I got this down to 40 lines of code and so much more performant than whatever monstrosity I was writing yesterday. Yeah, it's a wonder what a little bit of like clarity of thought will do. You sleep on a problem, think about it in your head. Oh, Fro, thank you for the raid. Thank you for the raid. What you just missed is I finished day 12, and I was talking about how it was last night. I got stuck on it. I just didn't have clarity of thought, and it was getting late, so I went to bed. And I went to bed and I couldn't sleep because I kept thinking about the problem. But like I was too tired to whatever. But I still thought better than I was in front of this because sometimes thinking without the computer in front of you prevents you from like thinking aimlessly. So I thought with more purpose. And I thought about basically this change to my approach. So this match ranges, I thought, okay, I should pull that out into like a separate function. But my memoization would be on counts, and I would sum up counts rather than, as basically instead of returning counts, I was returning, okay, this is the remainder string after you do a match, after you perform a match. And I was trying to memorize that, and that was not working out. It's running out of memory. Like with a count that huge, uh, no wonder. Like the strings are way, way too large. Um, so I wrote this up, and it felt so much smoother to solve this way. And what I'm going to do now is review some other people's approaches to this. Let's see. Let's pull up Discord. So Moon Sculptor in C++. It's not a native language to me. So we'll see what I can glean from this. Interesting. Okay, we have a bunch of templates. Interesting. Is this just for like speed with typing? I suppose. This must be like standard templates they use everywhere. Okay, let's try to get to where I don't think this is. Wait. What? What is all of this? Is this like a? I mean, it looks boilerplatey. Looks like that's not the core of the algorithm. IO. Not gonna lie, you got me scratching my head a little bit. Just out of like familiarity. Okay, but here's the algorithm. So we split a string. Oh, this is just a method for splitting a string generally. Okay, so this isn't specific to today to yesterday's problem. I guess it's still today's problem. Like 13 hasn't dropped yet. Um, generate all. There's a okay. There's a memo, and this is the runs given a string. um, I mean, I don't know what's represented with C++ code, but I imagine like this is part of the reason I don't write C++, is that I need like a higher level of semantics. Mhm. So this is compute. Compute what exactly? And what does LL mean again? I forget what L is. List of lists, I guess. And current run. Bunch of possibilities. Okay. Well, I'd hope I could get more out of that, but I am no expert there. Um, there is a Scala Discord, so we can see how other people did it in Scala. What do we have? Okay, like here's one. Day 12. Encrypt puzzle input. Oh, interesting. That's not one, but they've encrypted their puzzle inputs so that they're not accidentally leaking things. That's interesting. You're, the rule is you're asked not to commit your puzzle inputs to GitHub. It makes it harder to steal the puzzles themselves. Uh, that's at Eric Wastel's request. I wonder how fast mine runs. Let me just check that real quick. I don't know. Let's add like a 2 + 2 in here and reevaluate. Wait, that was fast. 0.77 seconds. Oh, I'm happy with this. Okay, let's look for other solutions. Other solutions here. People are talking about encrypting. Sure. I left 10 cores running brute force last night, and they made it 50% through by morning when I killed them. Oh, same idea. Don't do the same more core in once. Combine identical states. Okay, yeah. So pruning. Pruning is kind of an analog of memoizing. Okay, cool. There's an attempt I'll be happy to read. Someone else has utility code for memoizing, which I'll be happy to look at. Um, okay, here's a day 12 solution. And here's Seth's solution. I should have known by that sooner memoization has saved me before in AOC. I mean, I was thinking about memoizing from the start, but I just didn't know in what way to do it properly. Right? And here's another day 12 approach. And let's pull up mine as well. I'm day 11. We'll start with here and then we'll just edit the URL. And yeah, so here's Seth's approach. Seeing as how many numbers in a row we have just some, not numbers, how many damaged bits. Okay, so if states is empty, then this is our base case. We have something very similar for ours. Otherwise, oh, we're matching on the string. We're doing like a kind of a recursive descent parse. If dot, oh, I don't even trim these anymore. I used to like trim all of these in advance, all the dots, which I suppose would make my solution faster, but it's not necessary. Okay, so basically we can skip over, right, and then they're recursing with just that skipped over. Great. And if there's one of these, we start counting. So we count like how many we've seen in a row. Yeah, so this is like a recursive descent parse. And we parse each problem, and we do the matches, and we do the sum. So at some point here, we're also recursing on this vector of int. When is that happening? So we have calls to matches, base.tail, counts.tail. Nope, in this case here, counts, we're just passing along counts. When do we actually take counts.tail? Oh, yes. Yeah, once you have one of these dots, then you can progress on to trying to match the next one, I suppose. Is that the only time, though? That doesn't completely make sense to me. But I see the general approach. Great. So that's Seth Tissue's approach. Nikki is a fast one. So we have a solver class tab. I think this is sort of a memo. What is a request? A request. Okay, list of characters. This is our our record. And then this is our group sizes. And int, this is probably like where we're starting from. There. Damage group is less than 0. Okay, and where are they using? Wait, where are they memoizing? Are they memoizing at all? The def compute continue group. Where's our compute function? Tab.get s.get or else. Okay, yeah. This is the one that uses the tab. Top-down tab. Maybe I don't completely understand what the top-down tab is, but to me it looks like memoization. They could use get or else update here. Like, I know, this case here. It's built into the library. Okay, that looks good. This is the code for memoizing functions. So you memoize, you pass a function, it creates a local cache here, and then when it has an A, we use this cache get or else update. Oh, wow, I didn't think of this, but yeah, this cache is in the closure. So this it's part of the closure from this A, from this function that's being passed. So this function itself that is returned from this A to B function has state. That's interesting. I hadn't thought about, I mean, I guess I sort of thought, I just kind of thought that was not possible. Okay, that's very cool. I should add a trick like that to my own library. And then here is someone's third attempt. I feel you, bud. Da, da, da. So they have a sealed trait. This is a use case for Scala 3. Like this, just these are just enums. So folding state groups, previous condition, there are copies. Push. So if it's operational, we do a previous match. Oh. Previous condition. I feel like this is overcomplicating it. So we take the next groups. If there are remaining groups to handle, right? And then we apply, we create like a new folding state. So this is like an intermediate state. Like this is what gets sent and memoized in my case. Backing. So is this like a backtracking parse attempt? It's unnecessary for here. I mean, it's as you see by other approaches. And I do struggle a little bit more to understand this one. And it's 140 lines of code. My solution is 40 lines of code. I'm so happy with this one. In fact, let's share it myself with the Scala community. After brewing on today, I started again from scratch. Got it clean in 40 lines of code. Runs under 1 second in Metal's worksheets. Wonders what a night of sleep will do. Yeah, it did feel so much easier. I wish I could have solved this in 15 minutes yesterday. I mean, I didn't solve it in 15 minutes. Like, I thought about the problem. I wish I'd spend 20 minutes thinking about the problem last night and then solve it in 15 minutes. Wouldn't that be something? I don't know. Maybe I do that tonight. Maybe I do that tonight. I'll remember to stop and think. And geez, I logged on so early because I expected this problem to take me some time. Now I think I have time for like more warm up. I'm gonna set up my day 13. So we're gonna save this worksheet as day 13. Make sure it runs. By the way, Metals got a huge update today. Metals is the plugin I use for like editing Scala in VS Code, and it's what lets me run these worksheets and whatnot. And today, it finally has full feature parity between Scala 3 and Scala 2. So I could pull up that blog post if, I mean, I find it interesting. I'm not sure how many people in here are Scala devs, but it's exciting to me to have, like faster type completions, more accurate, etc. Let me see if I can pull that up. Metals, is it like 3.2? Changelog? Metal Scala blog. Let's look that up. This one right here, be 1.2.0. So we're now using the presentation compiler rather than the semantic library, which means things happen kind of more live as you're typing. There used to be had to be like I don't know, like you save the file, it runs, um, and then like updates the semantic DB. But now it happens more instantly, and it can work with like when some of your code is inconsistent, right? Like compiler errors elsewhere in the file won't prevent things from being updated properly. Hmm. So I mean that's huge. That's huge because like I frequently have other parts of the file not compiling quite yet, or like I want to. And tree view. I don't know if you're familiar with tree view in other languages, but searching via package class structure and into dependencies as well. So that'll be nice to have. I mean, it's less relevant for where I'm using it here, but tree view is cool. Go to definitions for Scala doc. That's cool. Custom project root setting, a bunch of other features. But essentially, a lot of good support for Scala 3 added. Now we have full feature priority, and I'm much happier for that. Okay. I think this is a good time to go back into my library. Han Sohai to stop by. IntelliJ has better. I know it does. Um, I don't like using IntelliJ though. I prefer my heavyweight apps to be Electron. I don't know. I came to VS Code as a like an Emacs refugee because Scala 3 support in Emacs was starting to lag behind. Um, and VS Code was easier to kind of meld to my old Emacs ways, get, at least like key bindings or whatever working. IntelliJ has always been, I don't know, I've struggled with configuring it to my liking. Um, anyway, this is day 13. I'm just getting my file ready when the problem drops. Make sure that she's working. Please don't repeatedly request this endpoint. And when we last left off on my advent code library, there's a to do. Oh yes, so we're doing like a diff function between areas. So take one area and subtract another area from it, and you might get a list of other areas. And I wrote my first approach to that, and it wasn't quite right because I was only getting the areas of the four corners. So let's pull up my tests. Point tests. Area diffing. Okay, so when I subtracted a small area from from a larger area, I just got the corner pieces. So here we get all the x intervals. I think we should include. Okay, so we have a, which is what we're subtracting. A was going to be the smaller x range. So when you subtract that from here, then we are not going to have that a range anymore. So we have to add that back in. So plus a dot x range, I suppose. Or we could cons that on. So I believe this returns a list. Okay, so a dot x range onto those two, and then a dot y range onto those two. And now this would give us 9 areas, which is why I had this check in here. Because if we get a dot x range and a dot y range, we get exactly the a area. So I'm going to filter those out and yield all of those. So that's a very easy fix, sort of. What's going on here? X interval, object equals. Oh, this needs to be an interval. I will just wrap that in an interval. I'm conflicted if I should have all my own built-in areas. They're based on the base Scala range, but I like to use my interval type. um, right, like this doesn't always make sense with every range. For example, if a range skips ahead by 2 each time, a lot of these functions are just not going to make sense. So we'll think about that, but for now, we have to wrap these into intervals. I think one thing that's holding me off is that my interval type doesn't have all of the ccops methods that a range would have. And maybe I should just extend ccops. Not sure yet, but we'll see. We'll see. um, anyway, let's look at our tests. So now, what? This should rerun. Okay, now if we subtract the mid area and then and then sum up the sizes of all the areas we get 96, which is the same as taking the area or the size of the large area minus the size of the smaller area. So that's a good check. And each of these, we have 8 areas printing. That's beautiful. I don't know. Maybe this comes in handy today. What else do we have? We could take a union of 2 areas, which starts get hairier. I don't think I even have a union of 2 intervals. I think I should start there. For one, I could move a lot of these tests over to a new file. But for now, we'll just keep like tagging stuff on. This is kind of like a hacky way to do tests. I'm just doing them inside a worksheet instead of using any testing framework. Which, you know, kinda works. Archimal, thank you for the follow. And Jaguar Vision, I missed your notification earlier. All right. Let's take a union of 2 intervals. Class interval. And in 2 dimensions, I guess this is fine. If these don't overlap at all, we could end up having a list of 2 intervals. The union also ends up with lists. If they overlap somewhat, then we still need like a disjoint set of ranges. I guess if they overlap somewhat, then it just becomes the broader thing, right? But then you can take now you can take like a union of a bunch of ranges. Which is what might have to happen like when we start moving into higher dimensions. Okay. Def union. So we have another interval. I don't know why I've named it R sometimes and other times. I guess R is a holdover from when this was called range. But N could also mean like N, our integral type. Yeah, sure, R for interval. And this is autocomplete code and is not correct. So if do I have like an overlaps function? I guess if the intersection, if this intersection is not empty, I think I should just have an overlaps function. Da, da, da. Is there a better name for that? Is it like, how would I do this with like normal lists? I mean, I guess what I would do is take the intersection of those two lists and see if it's empty. I just don't, I guess this is fast. My intersect method is fast because it's only operating on like the min and max values in each interval, right? Yeah. So, so we intersect R, and if it's empty, um, or if it, yeah. So if intersect R is empty, then we have a list of this and R. And I wonder if I shouldn't keep these sorted. Like I've been thinking, I should have a super type or like a collection that is represented by a set of discrete, non-overlapping. What's the right word? Anyway, they are non. Oh, there's a word for it, but I'm blanking. Non-overlapping ranges, right? And then now you could take like the diff and intersections of those sets of ranges. You could have a type that represents like the empty range, and then all these functions, like some of these, this returns an option interval that makes sense. This you diff two intervals, you get a list of intervals, right? With like a normal Scala collection, and this is part of why I can't have this extend CCOPS. So like if we take list 3, 4, 4, 5 that intersect another list, 5, 6, 7, what we get is another list, right? So I want to have some type representing a list of intervals essentially. That is a return type for all of these. So like an interval set, it's called a range set. I feel like there's like a technical term, like a union, uh, wiki union, uh, disjoint set data structures, union find. Yeah. Okay. Yes. 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 This is essentially like a union find. A disjoint is the word I was looking for earlier. Data structure that stores a collection of disjoint, non-overlapping sets. Right. Where in this case, my sets are ranges. So they're very efficient ways of representing a large list of numbers. So we will eventually do a union find. I'm gonna link this. Leave this in the comments so I don't forget this time. To do and what is it? A superclass superclass of interval that is essentially union find. And that will be fun to implement. Okay, so we return the list of this in R if there's no overlap. Else, we do this thing. And again, like you take the union of two intervals, you get a list of interval, which is not like pretty. So interval min min r dot min max max r dot max. Sure. What is it not liking about this? Found a list. Oh, right. This returns a list of interval. Yeah, I'm gonna make a union find data structure. and it'll be awesome. Okay, so we can do a union of two intervals. I want to try a union of two areas, which starts to get hairier because there might be like multiple ways to represent that, right? Let's say you have two big areas overlapping. So you can keep the larger area, and then you can break the other one into rectangles. Should you keep the larger area? Maybe you should keep the smaller area. I think the larger the areas you keep, probably the better. And it gets difficult to determine. Um, I don't know. It starts to get tricky to determine whether two areas are equal, or rather two lists of areas, right? Basically two lists like 2D union find. Oh man, right. If I go down this union find path, then my areas themselves will start to be like a union find kind of thing. I mean, I suppose I could normalize it to where I diff each against the other. And for each of those diffs, you'll break them down into smaller. I don't know if I were drawing this, um, they share boundaries all the way, right? So like if this was a larger rectangle, it wouldn't go further above. Um, so the union of two that are overlapping the center would turn into 7 squares, right? The top 3 corner squares, these 3 corner, areas, and then the middle area. And that's the simplest approach. So let's try that. Uh, Def. So we have intersect, we have diff, def union area, list of areas. Great. So val this diff equals this dot diff a. And then a dot diff this, and we do their intersection. So this dot intersect a, and then to list and we just, yeah, concatenate all of those together. And then area union tests. What does this look like? Oh, I should do more tests on my diff, make sure that's working in other cases. So, reminder to myself. Well, top left area, we'll just say like, let's say 0 to 7. And then we have the bot right area, 3 to 10. It knows what I want to do. And then let's take the union of those two. So top left area dot union bot right. And I guess we'd map size dot sum. Sure, that's one thing to do. Dot map dot size dot sum, and it should be top left area dot size plus bot right area dot size, and you subtract the part that you counted twice. So top left area dot intersect bot right dot get dot size. Sure. And this is 139, same as this. So the areas are right. I'll just print all the areas. Right, we get 0 to 2, 3 to 10, 0 to 0 to 2. We have a 0 to 7. Why is there a 0 to 7 in here? Kind of want to like draw these and then like color it based on what area it's in. Um, yeah, this is like a big rectangle. Interesting. There are 7 pieces though, and the area is correct, or like the size. The size of the area is correct. Um, I don't think these are overlapping in ways we didn't want. So 3 is 7, 3 is 7. That's the middle one. 3 to 10, 0 to 2. That's a wider one from the top, and then 0 to 2. Okay, that's like a wider rectangle on the top right. That looks wrong to me though. So we had 0 to 7. Yeah, our top one is like 0 to 7. Our bot one is 3 to 10. The bot right one. Right, so how would you get 3 to 10 and 0 to 2 together? 3 to 10 and 0 to 2. This can be in the top right corner. Hmm. Okay, and then 0 to 2 range. Oh, that's the one I'm looking at. So 3 to 10, 0 to 2, 0 to 2, 3 to 10. Oh, I think this is accidentally working. Right? Like these two areas are exactly the same thing for one. Yeah, that's not what I expected. Expected areas. So let's make this. And I don't know if autocomplete can do this. I doubt it. So 0 to 2, 0 to 2. Yeah, that's in the very top left. And moving to the right. Oh, well, let's move down. So 0 to 2, 3 to 7. Exactly. And 0 to 2, 8 to 10. That is not expected. So this is going to be out. And now down the middle, 3 to 7, 0 to 2. So down the middle, there should be 3 squares. And down the right side, there should be 2 squares. 8 to 10, 0 to 2. But this is what's expected. And expected areas dot toSet should equal top left union bot right toSet. And this is false right now. Okay, so what did I do? I subtracted the right area. I call this A. I should call this like right, and what we're working with is left. Maybe this and other. I subtracted the other area from this. And what I should get, in fact, let's look at just that. So, yeah, just testing things out here. Let's say top left area dot diff bot right area. And we should get 3 squares, which are going to be like the top 3 corner squares, right? Each print line. Okay, so 0 to 2, 0 to 2, that's the very top left square. 0 to 2, 3 to 10, that's the middle left square. And this is the top middle square. So that's right. And if we swap this around, swap words, I hate that I can't swap words. Okay, and then this should be the bottom right 3. Okay, so like that's giving me what I expected. This dift and a dift. Why is it that when I add those together, and the intersect should be just like 3 to 10? Okay, I see other streamers are coming online. It's almost time. This is our next to-do, next time we're working on our library. And views might be buggy. And this is still not fully tested. Note, still not fully tested. Okay. I mean, will I see those? I won't see them, but I feel bad for having written that I still haven't fully tested them. Yeah, let's go back to our day 13 worksheet. And now's the time of day when we twiddle our thumbs and watch the clock. Oh, let me check. How am I on leaderboards? I've fallen behind. I'm still holding fifth, I suppose. I can get ahead of Jan Peter. There's Nixie and Alexander. These two, there's no getting ahead of them. But potentially I do some sort of catch up. And for the Scala Center, I'm back down in second place, and this gap has widened. So we'll see if I can get Jan Peter on that eventually. We have 50 seconds left until the problem drops. I'm excited. I'm still kind of high from solving 12. Hmm. And I'm right to get that input. 14, 13, 10 seconds left. 3, 2, 1, and day 13 is dropped. Let's just start by looking at the input. Oh, we have a bunch of maps. Okay, my areas will come in handy. Ah, interesting. Wow, a lot of shapes here. Okay. Cool. Locates an appropriate spring. We're on Lava Island. Do see a lot of ash. After a while, you make your way to Cluster Mountains. The valley is completely full of large mirrors. Most of the mirrors seem to be aligned in a consistent way. Okay, so this is a map of mirrors. You move through Valley of Mirrors. They're flat and shiny. Strange angles. Because the terrain is all one color, it's hard to tell whether it's safe to walk. You note then a pattern of ash and rocks. And as you walk, perhaps by carefully analyzing these patterns, you can figure out where the mirrors are. Okay. So for example, to find the reflections in each pattern, you need to find a perfect reflection across either horizontal line or between two rows or across a vertical line between two columns. Ah, I see. So there's a mirror here. And I don't know where it is here. Oh, it's like right here. Okay, we can reflect things. And it's always going to be in between 2 points. Second pattern reflects as horizontal. Okay, great. Pattern. So what's the question? To summarize your pattern notes, add up the number of columns to the left of each vertical line of reflection. To that, also add 100 multiplied by the number of rows above each horizontal. Okay. So we have several grids. Now, grids. Or, I don't know, let's call them the maps. And what we're going to return is a list of exactly maps, or we're going to do sets of points. representing rocks. Yeah, so these are going to be our rock maps. And return a list of set of point. Import ASC dot star where my points are. We're going to use mutable input today. So let's say we can get a map out of this. So like a parse map function, input dot take while dot non-empty. So you have a bunch of lines for each. Yeah, I'm just going to list this up to list. And then we're going to take an area. I think I'm going to take like a list buffer. LB collection that mutable that list buffer empty set of points. Maybe I should also return an area. Yeah, set of points with their areas. And then maybe we can do like while input that has next, and we can do a bunch of stuff. The grid, take while non-empty to list exactly area grid points. It knows what I need to do. Not just the area, but the points themselves. Val A equals area grid, and we're going to do like a dot points iterator. And yes, we're going to collect the case. How does it know that I want? Wait, is that exactly what we want? Left. So val points. We're going to do a dot points iterator, and we're going to filter. Filter grid of that point is equal to that, and to set. And we just return points in area. Points to area. We're just going to rename this A to area. And yep. I don't know what this line here is, but we're going to do LB that result. Oh, you know what? We're going to make this a vector. To vector. There we go. Points to area. Just a set of points. Wait, but LB. Oh, wait. Set of points and area. There we go. We need, that's tuples, we need parens. Okay, parsing was a little bit slow, but now we have these. So rock maps dot head. Let's look at the first one. Yep, set points. And we find mirror. So given an area and points. or rather we should do it in the same order. Points and then area. And then this is going to be an optional int index. And I suppose I could like flip each of these over. Or I could flip over the whole thing and just do it until, so let's say I have something, I flip the whole thing over, and we keep juxtaposing them, or putting them over each other, until we find a point where there is no point that gets diffed out by the other. The val flipped equals area cup, not quite, points dot map flip x. There's no flip x. We're gonna flip this point across an area. So this is gonna be like finding vertical mirrors. So we take a p. Yes, area dot right minus p dot x. And in fact, let's try this. So val points area, and then we take this here, a triple question mark that, and then let's do like an area dot draw. Yeah, and we're gonna draw it flipped. If flipped. Okay, so this one here, are those flipped across the x-axis? I think they are. No. I think we need to look at both of these side by side. So we'll copy the worksheet output, we'll go scratch. Yeah, they do appear to be flipped versions of each other. Okay. And then we look at overlaps. I mean, do we need to like binary search any of this? I think we can just brute force it. Yeah. Basically, if you take two sets of points and then we diff them, like remove one set of points, and then we union that back against the A, it should be the same set. Then that means it's exactly the same points. Yeah, I don't think this is a day where we need like especially a lot of performance. So our flip method works well. Val shifts. So what's this going to be? 1, 2. We don't want to shift it all the way to the size. What we do, we need at least one. 1 to area dot right minus 1. And shifts dot find. So we're going to find a shift such that well, okay, we define shifted. Shifted was flipped dot map. Not quite. So we take the p, P, oh yeah, P dot copy X equals P dot X plus shift. Oops, dot X plus shift. That's it exactly. And then shifted dot diff diff points dot union shifted is equal to the whole union together, right? Wait. Shifted diff points and then union back points equals shifted dot union with points. And whatever that index is, it's a flip. And I guess that in terms of these lines, so if the shift is 1, we flip it over, we shift it 1, what does that mean the reflection is? So we flip this, we take this, we flipped it over, and then we start here, we shift 1. And if there's a lot of matching stuff here, then that means the mirroring is happening here. Am I going to miss something if I do it this way? Okay, so like looking at this example here. So if you flip this over and we shifted, after we shift it 5, 6 times, then that bit in the middle will overlap, right? And then the fact that that overlaps makes our union diff thing true. Yeah, and this is the number of times you shift it, so I'm happy with that. So let's do like rough maps map, and then we're going to transpose and then find the other mirrors. This is finding a vertical mirror. And where are we going to map to? So we're going to do like a list of, I don't know, option int. Yeah. So we have points, area, val vert, and which gets multiplied by 100. Add the number of columns to the left of each vertical line of reflection. Okay. So the horizontal gets multiplied by 100. Find mirror points area, val, horizontal. And is it either or? I'm going to assume for now it's either or. Let's see. Now transpose equals points.map. Exactly. Transpose points, I guess. And then val transpose area. Area dot y range followed by area dot x range. Okay, that works. And val horizontal is, oh, there we go. It knows what I want to do. Let me just return vert and horizontal. And then val ends 1 equals, so val vert, or is one of the, this is called mirrors, equals mirrors unzip. And now vert is a list of optional int. We're going to flatten, not flatten, and vertical. No, horizontal gets multiplied by 100. So horizontal, that flatten, that sum, times 100 plus vert dot flatten that sum. Okay. And barring any like off by ones, just we'll give that a try. Okay, there's probably an off by one in there somewhere. So let's test this on a thing. Here's an example. The first one is vertical, the second one is horizontal. And we'll use this to debug our off by ones. So day 13, 2023. We'll save this as example. And we'll operate on this example. Okay, so the mirrors. The first row has some one and some one. Oh no. Okay, so let's do find mirror. Let's look into this. It is working right away. So diff points mean points. Look at diff the points they have in common. Why might that happen at 1? So for example, the first one, again, the left one is vertical. I should do horizontal and then vertical. Yeah, I'm just gonna switch. No, I'm not gonna switch anything. I'm gonna switch it. Horizontal, very cool. Just because that's kind of the magnitude order. Okay, so def find mirror, and then we're gonna do like what is it? The grids. So off maps head. And this is not def. This is just finding that mirror. And I want to draw each of these. So let's see. This is the first example, right? This, and then we flip it vertically. Oh, and then when you do shift it by 1, yes, it does. It does. Yeah, shifting by 1 is correct. So that's the right index of how many times you shift this over. But then you need to find the center line, right? So normally a center line, what is the area of this? So this is 4. I think. So this is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? It's 9 in length. And we flip it over and we shift it at 1. And the answer here should be 5. 5 to the left, 5 columns to the left. So because we shifted by 1, let's say we have 5 and 5 instead, right? So 5 flipped over, we shifted by 1, we found something. And this point here, how do we find this point here? I guess we count columns until there are an equal number of columns on both sides. 1, 2, 3, 4, 5. Right, like if we shifted by 2, it would kind of also be well, the intersection point here, it just becomes 3. How many columns from the left? Let's say this is the original. 3. And in this case, there's still also 3. Why? If we do it like here, that becomes 4. And this becomes 4. I think it's like a divide by 2 case. So it's based on... I need a formula. Okay. Move over, shift 1, 2, 3, 4. And when it was like perfectly whatever, there's not going to be a line. So it's always going to have to be these even shifts, right? So like this, actually, this is going to be like by 2. By 2. Yeah, right. So it's always ever going to just be like by 2. So shifting 1. 1 is the minimum shift. Right, I'm just going to do a quick test here of the data. And we get to do like rock maps. Map. We're going to get the areas. Dot x range dot size. Yeah, let's do that. They're all odd. So we're going to shift at least 1. And in that case where it's 1, it's just going to be like the length. So 9 divided by 9 minus 1 divided by 2, or no. So 9 divided by 2 plus 1 plus the shift. And if we're shifted even further over, before it starts to overlap, then what does that mean? So let's say like we're overlapping at this stage. So at this stage, it's going to be like 1, 2, 3, 4, 5, right? Because there's going to be 5 remaining on that side of that too. So if we shift it over by 3, that's going to be 1, 2, 3, 4. The point at which, so we're going to be like the index at which the ranges have the same amount on the left side and right side. So 1, 2, 3, 4, 5, I guess in that case. No, like we already had 5, 6. Yeah, because 6 and 3 and 6 and 3. Great. How did we get 3? Oh my god. I can't math. I can't math. 1, 2, 3. We move it 1, 2, 3 over. And that means we have to keep getting more, right? So we get 6. 1 maps to 5. 3 maps to 6. a shift of 5 is going to map to 7. So let's just create a formula from that. So 1 to 5, 3 to 6, and then 5 to 7. And this is coming from like 9. So this is like 9 divided by 2 plus 1. And this is like 9 divided by 2 plus 4. No, no. This is a function that increases just by 1 per 2. So I think shift over 1 over 1 plus 3 over 2. And this is 9 divided by 2 plus 5 over 2. Yeah, okay, that's what it is. So let's do that. Where did we have that find? Okay, so val mirror shift. Good morning, Blue. Good morning. It is a good morning. So mirror shift divided by 2 plus area dot x range divided by 2. That should start to get me bare. Oh, dot map whatever divided by 2 plus area dot x range divided by 2. Not size, or let's say area dot right, the rightmost. Yeah, or I mean area dot size, or dot x range dot size. Okay, we're getting some things that make a little bit more sense. Let's go back to our example. Whoops. Oh no, you overslept. You overslept. Oh, Zara, good morning to you too. Great. So we're still getting, interestingly, answers for both. Right, like that first one doesn't have. I'm just gonna add in this by 2. Pretty sure that needs to be the case. And for the first one, F4. I think there has to be a +1 constant there. So we're gonna do like a +1. And sketching math. Okay, horizontal and vertical. Why does the first one have a horizontal mirror? I guess it has a horizontal mirror and a vertical mirror. Yeah. Okay, so for this one, we get 405. We're 810. I'm just gonna divide by 2. And that's, I don't know why I have to divide by 2. But you know what? Works, it works. So let's go to the main thing. Okay. 35137. Okay, not quite, not quite. So let's switch back to the example. So for instance, So, for example, we have this example. The first reflection find a perfect reflection across either horizontal. The first reflection is across a vertical line between the two columns. Does it not have horizontal as well? Um, every other column has reflected column within. This is a day where actually using grids might have made more sense. Great. The second pattern reflects across the horizontal line instead. How's the first one not reflecting across the horizontal line? Okay, yeah, that's where it is there. But we seem to think that reflects across 5. Well, wait, 5 is vertical, 4 for horizontal. Okay, so 0, 1, 2, 3, 4. That's flat out wrong. Does this condition not right? Shifted diff points. Add back in points. Um, so shifted dot union. About their intersection. So let's say, okay, so we have some points. Like shift them over. I'm gonna say I like the math for my. Let's check. For this one, it is 4 for the second pattern. So the horizontal so we're getting the right numbers here, 5 and 4, but we're also getting 4 and 5 for, which is not good. Not good. Am I doing it to the right thing? So mirrors. So we take block maps. We take points and area. Let's print each of these. So here we have draw for the first ones. What is this? Area.draw points and flipped. Which mix of our, and we're gonna reassign it. Rock maps 1. And we'll also make this a var. And we just do the same kind of thing. We'll hide our math here somewhere, I don't know, down here. And we're just gonna draw. We're gonna draw again. We're gonna draw both maps. Make sure we're getting the right things. Pretty confident we are. This is double definition. I guess we can't do it that way. Sure, we can do it that way. Why not? Okay, fine. Points equals rock maps 1 and area. Okay, so this is the second pattern. That is indeed the second pattern. And this is the first pattern. Oh, you know what? I think I need to diff it kind of both ways. Yeah, okay. A. o- Or, you know what we could do? Shifted diff points, union points should be the same as points if shifted at union shifted. Okay, that changes nothing. Let's print line how much it shifted, and then maybe draw what we found. Print line, air shift. I know. And we could draw it in here. So just do pass. Line shift. We could do draw area draw. If points be, then whatever. I guess we should draw the shifted. And then we're gonna have like an area. So area that bounding shifted. And then we're gonna do it. Yeah, okay, so we had the drawing. And we print line what the shift is. And this is what happens when we find it. So now we can do some debugging. Wait, what's going on here? It's not really updated. So we are doing like a find mirror in these. Oh, it happens in here. It's not drawing anything. Oh, it's working immediately. Yeah, shift of white. think I think this thing here might just be bullshit. So we subtract the points from points. Oh no. Yeah, shifted is a flipped and then shifted, right? So we have two things, one of them flipped over. And then we diff all the points that match. Like if these match, then adding it back in should change nothing. If this has extra points, or like if this has extra points, so when we diff it, there's gonna be something left. Oh, and then taking the union again. Okay, yes, I see what's going on. We're just selecting the first one. Let's think a little bit more carefully about this condition then. So let's say the intersection of them. If union was either left or right. Yeah, so now intersect equals shifted, intersect, whatever. And then our condition then is that if that union with the intersect equals diff and intersect that union, or like not diff, what's it called? Points that union intersect should still be the same points. Shifted dot unit. Okay, that is our condition. That's our condition. Okay, what are we getting now? Oh no, it's still the same. I'm trying to be clever here. That's the problem. If you remove the intersect, no. Okay, I need a better way to think about this. We have this. We want to make sure that the intersecting part has no special bits. If like we take the union of these two, there shouldn't be. I see. If we remove this part here, then this should look just like whatever. So let's do that. Points diff out intersect, and that's what we then diff from the whole union. Mhm. Yeah, it should be this intersect should change nothing when you union it with either the left or the right. It's no, but just the union part. So the middle of the union part should change nothing if you diff out just the left side or the right side. So we're gonna say left, well, just the left bit. It's gonna be like points, diff, um, intersect. Okay, yeah, points at diff. That should just be left points. And if we remove just those left points, the thing is, if the intersect is going to be smaller, right? Let's say they only intersect at one point, but they have a lot of leftover stuff. Then when you diff out the intersection, you're still going to get leftover points from the left that are somewhere in the union. Okay, what I'm going to do then is just search. We're going to trim. We're going to trim the area. So now intersect area. Okay, we have shifted area. Geez. Whatever, shifted area. Yeah, area to bounding off of those shifted. Great. Val intersect area. Okay, and we're gonna assume that that exists. Okay. Now, points filter intersect area contains. Wait, this works. Oh, okay, it has an apply method. Points filter intersect area should equal yeah, it's the ones of the in the intersect area should be intersection points, right? Equals intersect and shifted that filter intersect area should equal intersect. Okay. I think Okay, this is not contains. Spelling error. And this should be an and. Okay. Like it's messy, but like we finally have this. So let's remove this, multiply by 2, 405. There we go. There we go. All right, we figured it out. My God. I wasted a lot of time on an easy problem. What is this? 23592. 23592. Um, Interesting. So we have some edge cases here. Uh, is this test here not enough? I went the wrong approach. But hey, look, at least we're doing this thing. Oh, there's some for which you get none and none. I wonder what those are. Okay. Oh. So we find mirror, get those points, we transpose the area. So if they're both empty, then we can print line. Debugging. I suppose I could take mirror filter, whatever. This mirrors should be a function actually. Get the mirrors for a tuple, I guess. Or I mean for set points in the area. So in this case here, we print line points in the area. Yeah, let's do that. Be kind of nice if I had an index here. So rock maps. Let's zip this with index, not zip with index, not map. Now we have an index we can use. A big print line. No mirrors found for I. And this now needs a case. There we go. Wait, what? Oh, right. We aren't drawing anything. No mirrors found for 1, 4, 5, 7. Wait, why can't we draw anything? Is P like empty? Area or that. Let's print the area. There's 17, 0, 17. Where are the points in there? Okay, we have points, but no drawing. Oh, right. Actually, I have to draw. You have to actually draw that. Get to a print line. There we go. Oh, that's in here. And yeah, let's examine these. Okay, these are the ones that screwed me. No mirrors found for 1. We see a mirror here. Yeah, there's one at 4. I suppose instead of shifts, we could have iterated by like number of columns. Right, and then we have to determine, okay, we flip, how many do we have to shift it to get it there to check? I guess we have to start with shift to columns or columns to shifts. So this is a case. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so since the mirror is never going to be on, we start with a shift of 1. We flip this over. Oh, we have to start even further over. Yeah, we start with like a negative shift. It's gonna be like -7 or maybe -9. I mean, let's say you have 9, right? It's gonna be a -9 shift over. That's too much. You start looking at overlaps. So -7 is here. Yeah. Okay. So let's add in those negative shifts. Shifts. Negative area dot height. We're assuming this area starts at 0. And let's just do like +2. And I'll say until area dot right by -1 or by 2. Okay. Now let's see if we get any of these. Oh, now they're almonds. Wait, they're almonds? No mirrors found for anything now. Are we missing 1 if we go that route? It seems like that should be more of them. Negative area dot right. Hmm. No, +2. Until area dot right. Let's print these shifts. Okay, and now when you do find mirrors, we should print a shift -12 until 14. Until 14. But I thought these were like odd sized. Oh, okay. Let's just do, instead of my +2, let's just do +1. Yeah. Or rather, let's do like a 1 minus area dot right until area dot right. Okay, now let's see. An exact range, sure. Um, great. Now everything has value. Da, 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 da. What am I? I'm just removing print lines. And these are no longer necessary because they're just like depot print lines. 31296. So 31296. Okay. We are still wrong. You're still wrong. At least there are no values where they're like both none. Man, I thought this would be so easy. And then I did this right here. Part 2 is going to be easy though, because we're going to have a mirror algorithm that works. Da, 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 da. There's going to be like diagonal mirrors, aren't there? Mm-hmm. Mirror shift divided by 2 plus x. There, the x range that size 2 plus 1. You know, let's see what happens with the example if we flip these beforehand. So the example, we're still getting 405. 5 and 4. This would switch to like 4 and 5. Wait, I don't know what this area, not 4 and 5, 4 and 3. So let's just do like another map on this. I'm gonna do like a temporary horizontal flip and then a vertical flip. Yeah, I should have flip on my area class here. Oh, it doesn't matter for area, but for points. Map p to p dot copy a dot x range dot size minus p dot x. No, we'll do like max minus p dot x. And this is just a new point altogether. And then that's the area. Area. And area dot y range dot min plus py. Why would that be the case? That is still not max. Dot max minus py. Okay, we're just gonna flip everything both ways and see what happens here. Still get 5 and 4. I don't think that's the expected answer. Okay, so like this first one here. First, there are 5 columns, 2, 3, 4, 5, right? When you flip that across horizontally, then now it's 4 columns. That should be 4. Um, and am I flipping properly? I am flipping properly. Let's see what these look like. So area to draw the points. Let's just flip both horizontally and vertically. right. That looks right. And now it is 4. It is 4 over. The answer we should be getting is 4. And when we flip it, sure. And now this one. Interestingly, I don't think that is actually my. Oh wait, it's missing the top string. I see. Yeah. Okay. So determining if they have flips, we've done properly now. Is this big old thing, which I thought was going to be shorter. I thought it was going to be more clever. Um, but determining the actual shift, I feel like there should be a nice closed form for this. So we have the amount that we've shifted over, right? Let's say we've shifted over 5. We shifted over 3, right? The answer here is 4 plus 1. 4 plus 1 equals 5. So 3. 3 plus 1 equals 4. So um, that's how many it takes to get over there. How do we know that only one comes before the shifting point? I mean, because when we count from the other side, we have 3. Okay, basically, how many do we need to get 5, right? We need to get 5 points. We keep moving over until we have 5 points. Um, and so we subtract 3 from 1 count. So 3. So something. I know. This plus this has to equal 5, right? These 2 bits have to equal 5. And how is this related to this? This is going to be this minus 3. Like 4 minus 3. 4 is our answer. And how much shifted over? Okay, so let's say we're looking for 5. Need 5 columns altogether. One side of the shift. So we take the number of the columns that go to one side or to the one side plus columns minus 3 equals the total number of columns altogether, right? And we solve for that. So cols equals 8 divided by 2. Okay, so we take the shift and we do like area dot x range dot size plus shift divided by 2. There it is. There it is. We finally mathed properly. Okay, let's see what we get here. 4 and 3. Beautiful. Beautiful. That's it. Now we move that test there. Okay, 100% this is the right answer. 29165. About time. 29165. Okay. How'd I do 5,000? I was slow. I was so slow. But I know there's something I like about my solution in there somewhere. You resume walking and smack. You run directly into a mirror. You discover every member has exactly one smudge, exactly one dot, or whatever should be the opposite type. Locate and fix the smudge causes a different reflection line to be valid. Oh, I think this is easy in our example. I think this is I think this is easy. Basically, in this thing here, um, um, so it would formally match this intersect exactly. Now, when we diff it, there should be 1 point, right? So Al left diff. I'm just going to comment out this previous answer. Now, diff out intersect. And there'll be one thing that's off. I think maybe two, actually. Will that be two? I think there'll be two. Diff intersect dot size equals 2. Now, right diff. Okay, and we'll say left diff, right diff. We end up missing a bunch of things that way. Okay, so maybe the diff is just 1. Oh, and actually we might need like a union. Okay, if 1 point is different, taking the intersection, all the points are in common. And we diff that out. Oh, this is gonna be 1. This can be 1. Okay, try this. Boom. Well, 32192. I might have been slow on the first part, but fastest delta ever. 32192. Can't beat that. Ah, all right, all right. Oh, cool. So I'm gonna commit this and say this is how we solved on stream. Day 13. Commit and 2023 day 13 as solved on stream. Put that off to the side. Day 13 as solved on stream. And we'll do a little bit of cleanup. But I want to see how much time I made back. So we were 5,000 for 1. We dropped 2,000 ranks for part 2. Look at that, 3-minute diff. Oh, I'm so happy. Let's look at my leaderboard, which, by the way, oh, I'm gonna push this. Say my password out loud. Okay, so my code, if you'd like to see it, is up here. That's pre-cleanup. I'm gonna clean it up here in a sec. And this leaderboard I'm looking at right now, if you'd like to join it, there it is. So I was slow. I was slow. It took me a while to work out the bugs. But I was one of the fastest deltas. Oh, wait, no, this is a different day. 13. Okay. I mean, I guess I did take 3 minutes. Um, could have been faster. And part one rank has 12. Part two rank also 12. Hmm. Fine. I think I dropped spots. Nope, I'm still in the same place. See if we can make up time another night. And I'm still behind Jan Peter, but I'm further behind. So we catch up to him later. Let's do a little bit of cleanup. And I do want to see other people's delta times over here. Yeah. That I'm happy with. Oh man, it took me a while to figure out the math there. Um, hmm. Okay, points different. We're gonna say we're gonna have like a smudge variable here. Smudge int, and oh, we just apply the smudges. I kind of like this in principle. So find mirror. Now needs a smudge. Um, yeah, we could say def. Okay, we don't need any of this stuff here anymore. What's this else? Interesting. Um, Great, so def mirrors. So yeah, find mirror. I guess we have find both mirrors. And then points, set point area is an area. Don't need that anymore, don't need that. And this just gives you a tuple. So we find mirror twice. We apply a smudge. Smudge it. And just pass that along. So down here. Smudge. Okay. Oh, Bill the Gray, thank you for the follow. We've never looked at Scala before. What do you know about Scala? Um, well, this is Scala. In particular, this is Scala 3, so it looks a lot more like Python than it used to. And I think this here should be straightforward to understand. I'm not using anything crazy about Scala in here. I'm just cleaning up some of my code. Delete these constants we don't need. This whole thing can probably be simplified. This is my find mirror function. We don't need this test anymore. So we're gonna take mirrors of, oh, we're gonna take all of the inputs. So mock maps, I guess we call them mock maps. Dot map mirrors and smudge of 1, smudge of 0. Unzip, there we go. much. So this is my variable for like how much you're allowed to be off when you're laying your mirrors over each other. So for part two, turns out like your map's not quite correct. There could be there's like one dot that should be a mirror and one mirror that should be a rock, right? So this is just my way of making that a variable to switch between part one and part two. There's ands one, ands two, as a smudge of one. There we go. Yeah, now my find mirror function probably simplified. So we only really need the intersect area. Shifted area to intersect area. We could also I don't know. Intersect area could be area dot intersect. Never need shifted area again. Right. Bounding box of shifted. And then do a dot get. Here the points shifted over. Here's the intersection of the points. And now points dot filter intersect area. I wonder if both of these are in fact necessary, or if I can combine them into one. So points we filter intersect area contains. It should have, I don't know, this contains maybe be an apply method. Does it have an apply method? Yeah, and that tells you if like a point is contained by that area. I think I should add one. So def by p point equals contains p. I think that makes perfect sense because area is sort of acting like a set, right? I don't know if it's recompiling or not. Def by point boolean. Yeah, this is a function over points to boolean. That makes perfect sense. Intersect area is an area, whatever. I'll leave that as dot contains for now. I guess this works. This is like, it's long, but it's like explicit. It's kind of clear. I hope that's clear what the idea is. Right? Just being, remove all this test code, all these drawings and whatnot. Let's draw those. I don't know why this was imported. Don't need it. Yeah, okay, this is my code cleaned up. I think that's what I'll go with. Day 13. Yep. Push that. Okay. I had a few little wins there. I had a very fast delta. I got stuck on math that looked right. Okay, let's see. Let's do a quick recap here. This is partially for myself, because in the future, I'm gonna get a collection of all my mistakes on every problem here. Maybe I'll make a video. Maybe a blog post. all the mistakes I make, how I could avoid them, and how I could what's the word, mitigate them in the future. Um, what got me? Okay, here's one. I wasn't shifting over by enough at first, and this worked. But as starting from one and then going to area.right, and that looked like it was working because in the examples, the first few don't shift over, they don't flip over that much, right? So like the shift over is just very shallow. It could have been a lot deeper. This I debugged by testing by taking my test data and flipping it over horizontally and vertically to get new test data, and that's what revealed that. Um, this whole thing, at first I had like union diff union back, and of course that's always gonna be the same answer, so it's always returning true. I didn't test that properly. What I should have done is tested that off to the side somewhere before I just assumed that was right. It sounded right to me. I guess I got carried away thinking, oh, this should be super easy, just diff and then union back. And maybe there's still a clever way to do this. I feel like there should be something that's even more clever. I mean, in terms of like sets and doing like diffs and unions, but I haven't thought of it yet. And that's just, I know that's been tickling me from the start. I wrote one down and I thought that was it. What else? Oh, figuring out this formula here. There were easier ways to figure this out. I could have just like counted. I don't know. I insisted on having a closed form, and it took me a while to reason about this. I think the answer is just like get good at math. I just score this. It's not exactly clear anyway. Yeah, those were my big things. And each of those took too long. I'm gonna have to review my video and look at the parts where my reasoning was wrong, where it's taking too long to debug those. But this is at least a quick recap of that for myself and for you if you're interested, of course. And I I would like to review your solutions as well. So if you want to share yours, you can get to me here on Discord, or if I'm live, you can just paste something in chat here. But I'm curious to see how other people approach this. I feel like mine might be on the unique side. I think it's kind of silly to use a set of points. Often it is a smart alternative to just using the grid itself. Maybe. It did let me do this here, which was nice. So I do like my solution. I don't know what's all of your take if this is concise. I don't really have an idea of what other people's solutions are going to look like. I'll be very, very, very curious. Well, that's it for me oh, wait a second. You were working on something before this happened. I have a big to-do here, and I don't want that to get forgotten. The union might be buggy. The diff still needs to be fully tested, so let's do some tests. Point tests. In fact, I'll put the diff method on the right here. That I'm not blocking the tests. Tests. Okay, so here's a case where we diffed a small area from a larger area, and what we got back was this list of 8 smaller areas, the one that's above the corners, etc. Let's see. What if we were to have something like um, top left area and bot right area. Define these up above too. These are kind of like hacky areas or hacky tests. Yeah, let's do large area dot diff bot right area. And we should get a list of 3 areas. Right. Yeah, this top left corner, this top right rectangle, and then this bottom left rectangle. And you can see those are all present there. I don't know, let's do a few tests on these. So dot size equals 3. Dot map dot size dot sum, and this should equal large area dot size minus bot right area dot size. These are non-overlapping. 57. And then now we're going to take, I want a diff top left area with bot right area. So let's put it this way, bot right area dot diff. Oh, diffing large area should end up with 0. I mean, that's one thing. We could do like mid area dot diff large area is empty. Yeah. Cool. And let's take bot right area dot diff top left area. And the size should be 3. What else? Let's just take a look at these. Line. Do like map area dot sum. Okay, so these are the remaining parts of the bot right area. So 3 small squares. Let's do dot map dot size dot sum, and that is 57. And that should be the same as, well, their intersection removed from, yeah, let's do that. So bot right area dot size minus bot right area dot intersect top left area dot get dot size. That should be the same. 57. No? Why not? Oh, Medi, thank you for a follow. And welcome to the channel. Okay, I think let's just fix this real quick. Bot right area. Full size of the bot right area. Minus their intersection of these two, the size of that. The intersection is the only thing that gets diffed out, right? It should be the same as this. Look at what this intersection is. Yeah, it's area 3 to 7. And it's 25. Also hold bot right area that size. 64, right? Makes sense. 64 minus 25 is patently not 57. Interesting. So there's stuff to debug here. I was hoping I could just very quickly verify that this is correct. we might have issues for subtracting top left area. Okay. To fix this. Right, this works fine. Like, this is what we expect. Large area, diff bot right area. Oh, that's the remaining bits of the large area. 57. I don't think we should actually get 57 here. I think 39 is actually the correct answer. So, bot right area, and we're diffing out top left area. It should be the same. It should be the same as bot right area dot diff top left area dot intersect bot right area. Um, Interesting. Okay, let's look at what this is specifically. What we print line. We get the area 0 to 7. 0 to 7. The bot right area is like 3 to 10. Right? So our diff method is not quite accurate. Point diff. Diff on areas. Oh, okay. So we include this a.x range. This isn't quite the correct answer here. Like, this works. This works if you have, specifically when you're just moving a smaller area from a larger area, because you have to add these back in. But you actually add those in conditionally. I think so. We have to do a filter here. Like, each of these should be contained by the larger area. Maybe not. I mean, okay, so these we do end up filtering out, but we still need, like, so let's say we have a diff, we have our x range, and we diff out the other x range. Let's say this is A, right? We diff out this. We are remaining with this little bit, and then we also have that from the full a.x range. It'll be filtered out, so we don't care. We have that smaller bit. I should really do this. Maybe I come back to this when I have a tablet. I have a drawing tablet that makes things like this a lot easier to visualize and explain. So this is still buggy, a different area. Do not use, still buggy. Yeah, you can think about that. Think about what intervals are left over. Right, when you take out the small one, we just have the small interval here. We just have that small interval on top. And we take each of those in like combinations, right? This a.x range. Oh, a.x range is going to be too big because we're taking a.x range with that. That needs to be the intersection. This here needs to be an intersection. Yeah. I'll leave a note about that. Should be using intersections. I mean, what if I just do it? Okay. Yeah, we'll think about that next time. I think in code in one of my past solutions, I wrote something like this. That I could probably compare against that. And it might be fun to debug with a drawing tablet. So we'll save that for another time for another warm-up before another admin code problem. Let me find someone to raid. Let's see. Twitch admin code. PG impact is almost certainly done. Is Alka not done? Who else? Oh, Zombie Shoe. Zombie Shoe's doing admin code. Ah, okay. You know Zombie Shoe. They were in here earlier. Maybe we'll say hi to them. See how they're coming along. They seem nice. Okay, let's mute off the music.
Man, my eyes are killing me.
Let's
Okay.
start a raid.
So there's I'm trying to figure out where the new mirror is here. I'm seeing patterns everywhere.
Join stream. Let's look at who all time. Following that's on. And yeah.
Oh, here you go. Here's another pattern. Here's another mirror down here. Okay. So this should be a hash. This should be where it finds it, right?
All right.
You should see that
good night.
at this point,
and good luck with the rest of
I could put a line right here.
Say hi to Zombie Shoe.
And mirror. Okay. So let's do this. Paste. We'll call this input 2.